obtained a PhD in mathematics from the University of Utah, supervised by Stefan Petrikis. And she currently works as a preceptor and emerging scholars program administrator, as a preceptor and emerging scholars program administrator at Harvard University. So I'll leave you with Allechar.
Thanks. Yeah, so today I'll talk about this, and this is work in progress with Michael Allen, Renee Bell, Robert Lemke-Oliver, and Tiana Wan. And I'll just give lower bounds on the number of fields that can be generated by algebraic points on plane curves. So throughout the talk, if you see K, it's just gonna be a number field, and C is gonna change throughout the talk. So right now it's gonna be a smooth curve of genus G, and there is this very famous result by Faltings that says that if we have a curve of genus 2 or bigger than that, then the set of K rational points that we denote by CK is finite, and it's not only finite over K, but it's also finite over finite extensions of K. So we could ask, like, do we have finiteness results that are like this for higher degree points of the curve? And let's just define what the degree of this algebraic point is. Well, the degree is going to be the degree of the field extension that it generates. And in this case, KP is the minimal field of definition of the point P. And yeah, so as we know, like a curve of genus greater or equal to 2 may have infinitely many points of some degree. But it's still important to characterize when this happens. And there's here a couple of papers that do that for hyperelliptic curves. But there's another question that one can ask. And this is an idea that comes from Mazur and Rubin. And it's, what if we studied the fields instead of the points? So the idea is that we will study the set of field extensions, KP, generated by algebraic points, and those are points that are on the curve for an algebraic closure of K. And this is part of Mazur and Rubin's Diophantine stability program. And just to add to the definition, in the stability program, variety over K is defined to be Diophantine stable if the points over K and the points over L coincide. So we're just trying to see what happens with this set of field extensions. So if we have a number field and a smooth curve, again, we denote by KP, the minimal field of definition for P. So again, just to restate the question is, how many extensions do we have that are generated by algebraic points for a fixed degree and ordered by discriminant? So I need to define some notation first. So throughout the talk, we just will have counting functions. So big N of little n of x is going to be just counting the set of extensions that have degree n, little n, and the discriminant is at most x. And if we add this there, that means that we are counting the extensions that are coming from the algebraic points. And again, we want the degree of the extension to be n, and these are ordered by discriminant. But we could even ask more of this. And we can ask also what happens for extensions for a specified Galois group. So we add this condition of having the Galois group of the Galois closure of KP to be isomorphic to a specific group. And people have done counts for that, mostly for the symmetric group SN. So then I'm going to talk a little bit about what is known there, and then I'll prove the result. So what we already know, there is this result from Lemke, Oliver, and Thorne, and they prove that in the case of elliptic curves, we do have a lower bound on the amount of fields that we can generate. And this number here tends to 1/4 when n goes to infinity, but they also prove an even stronger result. And it is that it is stated here that the bound they have is also an asymptotic lower bound on degree n extensions, for which the Mordell-Weil rank satisfies that the rank over the extension is greater than the rank over Q for the elliptic curve with root number plus or minus 1. And again, this is important because we don't really know what's going on with the ranks, right? We know very little. So results about this give us a better understanding on are we actually in these algebraic points, are we actually generating enough points so that the rank will jump? And the answer is yes. And then Keyes proved this result for the case of hyperelliptic curves. And again, they found a lower bound for this with the constant again going to 1/4 when n goes to infinity. And there is some technical condition on what the polynomial should be, but really, again, we just have the idea that we are actually generating enough fields to get a lower bound. And we can also prove this in the case for superelliptic curves, sorry. So in all of these results, we can see that, for example, the statement that is proved by Lemke, Oliver, and Thorne, there aren't a lot of conditions on n because an elliptic curve has a very well-defined equation. We can solve for y if needed, but the more that we are going to relax how our curve looks like, then we have to put more conditions on n where n is the degree. So in this case, for Benetian Keyes, in the case of superelliptic curves, they do still have some structure, but they need n to be a multiple of this max of the LCM. And why? And this is because if we have a degree that is very small and our curve, for example, has very high degree, we can't make sure that we are actually going to generate that extension, right? So we need n sufficiently big, but we also need it to be so that we can actually write, so that this is actually parametrizable, right? So in the more that we just relax our conditions, the more that we have basically no idea of how the curve is going to look like. And then we just have very crazy conditions for n that sort of look like this, and always sort of in terms of the curve that we're using, or the parametrization that we're using for the curve. But again, Benetian and Keyes do find that there are enough curves, enough extensions generated by these points on these curves, and this upper bound is now this c is going to be 1/m², where m is this degree of this map that is just mapping points from the curve to P1. And in our work, we find the same bound, sort of like that Benetian Keyes found, where m, so like if we have a polynomial curve defined by this polynomial, and then m is the minimal degree in x or f, in x or y of this polynomial f, then for an admissible n, and by admissible, I'm just gonna leave it like that, and that is just well behaved, like it's big enough, then we do have 1/m² number of fields that we can obtain by algebraic points. So again, the condition on n is going to be kind of technical, But the idea is that we have enough fields. And not only that, but we also have proven a condition on the Jacobian. So if we have a smooth plane curve and we have the Jacobian, then for n greater or equal to 2, there is a constant so that the rank of the Jacobian is actually where the rank of the Jacobian over K and Q is the same. So we have a cardinality for that set, and that is going to be at most C of little n little c, big C. So again, this is just trying to prove an analog of the condition that we have for elliptic curves. And because our curve is more general, then we have to look at the Jacobian and the ranks that they have. But this again gives us an idea of how the rank is behaving. So are there any questions so far?
I have a small question that you might not be able to answer. But earlier you said that the constant for, I think it was elliptic curves, like was approaching 1/4 from below. And then you had the constant like 1/m squared, right? Like Cn was approaching 1/m squared. Is that also from below? Like, is that some significance to this from below thing?
I don't know if it's approaching from below actually.
Okay.
Yeah, and this is because the proof is still in progress. So like we actually haven't even computed like the fudge factor and like the constants. So okay.
I'm sorry, I have a quick question about the slide you were just on.
Yeah.
Okay?
Yes.
So the previous one, so how far, because you said that the cardinality is at most CNC, like how big is the gap between the actual cardinality? Like, is that set ever empty, or is it, or like, is there a big gap between the actual size of that set and your upper bound for the cardinality? In practice, do you have examples to compare?
I don't have examples. I think that the gap should be big, right? Because like all of these are asymptotics. So again, we just have that it behaves like x to the n to the c, but we don't really know. Like we just know that the difference is not big enough that it would show up in the factor of x, but it can be really big, right?
Allechar, can you hide the pencils there, the color pencils, so maybe we can see the screen?
Oh yeah.
Nicer. Thank you.
Is that better?
That's good.
Okay. Okay, so the strategy of this proof is that we're going to use the equation of C to find an explicit family of polynomials, or at least as explicit as we can, generating this degree and extensions. And then we showed that these polynomials are going to be irreducible. And then we have to take into account for multiplicity. For example, are the polynomials actually different? How many polynomials are generating the same field? And so on. So what do we mean by n admissible? And this is going to be related to the degree of the parametrization, the polynomial that we're going to use to parametrize the curve. So we have an algebraic curve, and then f, like curly f, is going to be the set of fields defined by the algebraic points on C. And we're going to say that n is admissible if actually we get an extension that is coming from an algebraic point on C. So the parametrization, we're just going to parameterize x and y as rational polynomials with integer coefficients, so that we can write f in this very, very pretty way. And then we're going to say that n of that parametrization is going to be the degree in t that we actually get out of f. And we don't necessarily get the degree that we want, because this could cancel out. We don't know really what the parametrization is. So the degree is not always what we expect. And n is going to be called parametrizable if we can actually get a, b, C and D, and these are the degrees of the polynomials that we're going to use for the parameterization, so that, you know, this n is actually coming from that parameterization. And the goal is to characterize the parameterizable integers and prove that these parameterizable integers are actually the ones that are in the set that corresponds to the ones, to the extensions that are coming from the algebraic points. So, and I apologize for this horribleness that you're going to see, but this is what happens when one does arithmetic statistics. So if we have a curve that is just a polynomial on two variables, so we can write it like this, then we're going to take all the ordered pairs ij, so that the corresponding numerical coefficient is not 0. And then we're going to consider the convex hull that those points define. So we have to prove certain things about these ordered pairs. So we actually have that if we have a fixed point of the convex hull, then the following things are true. So that vertex is going to be actually the vertex that gives us the maximum, the actual degree of the polynomial. And that is just going to depend on a minus b and c minus d. Again, so we just want the achievable sort of like degrees that we can get to depend on the parameterization. And the order pairs a minus b, c minus d, for which the point, the vertex is actually the one that gives us the degree of the polynomial, are going to be actually the integral points in a cone. And then the order pairs for which it is a non-strict leading term. So that means that there is another coefficient that it could be also the leading term, or that they have the same degree. These are going to be in the boundary, and the cone is big enough so that we can fit an L by L grid for every L. So, I mean, and what is this cone that I'm talking about? So if we have a convex hull, then we have the point here, I0, J0, and that is going to belong to some sort of, convex hull there, and there's going to be points here. So then what we're going to do to like build this cone is that we're going to take the normal vectors that are here and here, and then this is gonna sort of like define a cone. Like if I do this sort of and then extend it, then it's gonna generate a cone. And this is the cone that I'm referring to here, that is actually parameterizing that is actually giving me a description of how do the leading terms in the parameterization are going to look like. And again, these vertices that are in this convex hull are coming from the parameterization of the polynomial. And the other proposition is that for a vertex in the convex hull, then the quadruples for which that vertex is actually a strict leading term can be made, then the degree of that parameterization can be made equal to any sufficiently large multiple of this GCD. So again, we're just trying to figure out how big do we have to go in the extensions for us to get enough extensions, because extensions that are small compared to the parameterization that we have are very problematic. We cannot make sure that we actually get them because we are constrained by how the curve looks like. Or
can I ask you a quick clarification question?
Yes.
So when you did like that yellow kind of line, like for a second, you kind of drew over it. So was that like perpendicular and in the middle of the segment?
So what is going to happen is that we actually are going to move the cone so that it is in this quadrant, actually, so that we get sort of like a normalized cone.
Okay.
Yeah, so that it wouldn't matter where the convex hull actually is. Yeah.
Right, but not just in terms of like where it is, but like how big, you know, the angle is. Like you get it from going like halfway and then perpendicular and seeing where they hit, or am I misunderstanding how the cone is even defined?
I guess like this is going to I guess, yeah, it should be the one that is in the middle, and then so that you don't, yeah, because there are many, you know, normal lines. So yeah.
Right. Okay, thank you.
Okay, so then once we know like which ones are the ones that are admissible, then we need to prove that the polynomials that we have are actually irreducible, and that we get what we want, that we get the degree extensions that we want. So then we prove that the parameterization that we get is actually irreducible in these two fields. But so far what we have done is that n admissible is determined in terms of the curve, that we have conditions on the degrees of the parameterizations that we're using. Specifically, we have conditions on a minus b and c minus d, which would be the degrees in T of X and Y that are coming from this construction of the convex hull that have to be satisfied to make this parameterized degree have a chance to actually be equal to n. And then because we have these conditions, then we can choose A and B as small as possible, satisfying these conditions. And then for any C and D for which the parameterized degree is n, the parameterizing polynomial that we get is actually going to be generically irreducible. Okay, so far we have a description of n in terms of the curve, and then we have proven that the polynomials that we get from this parameterization are irreducible. Okay, so then what is going to happen is that we have this lemma. So if we have this polynomial and we assume that we actually cannot write it as phi1 of just t and phi2 of ty to the k, with the degree, with the polynomial being linear in y, then we can take C and D non-negative, but at least one of them has to be positive. Then there exists non-zero constants, and this is the constant of the polynomial, so that any given polynomial h of degree n greater than 1, we have on, big O of n choices for the polynomial C and D, and the degrees are going to be little c and little d with the leading coefficients that we actually want. So what does this lemma prove is that, well, it shows that most specialized polynomials will be different. And why? Because the choices that we have here are, we have a lot of choices. So again, this is just sort of like after we have figured out that the polynomials are irreducible, then we actually need to prove that they're different polynomials. Okay, so now that we have put together basically all of the conditions that we need, we can do the counting. So what do I mean by this? Well, we actually need to count how many polynomials we have, and then we need to get rid of the ones that are actually the same, which, you know, we just did. And then we actually have to get rid of the fact that some polynomials are giving me the same field, right? So we consider all polynomials, big C and big D, with escalating height at most h. And by escalating height, we mean that the coefficients have to be, the ith coefficient has to be smaller than h to the I. And this is for both C and D. So then the parametrized polynomial will also have escalating height h. And why is this? Well, because sums of polynomials of escalating height h will also have escalating height, O of h. And the escalating height is the same as the roots being of absolute value big O of h. So the products are also good because the roots stay between, they're going to be at most O of h. So now this means that how many polynomials have we written down? Well, we have written down this many polynomials. So up to degree h, right? We have written not only C polynomials, but we have written for every degree that we're choosing here, right? Because we are we're adding up to C, the choices that we had, and then up to D here. So then we have this many polynomials, this many specialized polynomials. And then what do we do next? We need to apply Hilbert irreducibility to make sure that these ones are irreducible and they actually are cutting degrees, fields of degree n. So Hilbert irreducibility sort of like told you that if you had found a parametrization that gave you an irreducible polynomial, then actually almost all of the parametrizations will give you an irreducible polynomial. So in our lemma here, let me find it. In this lemma here, we actually, made a choice so that the polynomial that we got was irreducible. So we found a specialization of this polynomial that was irreducible, and Hilbert irreducibility tell me that if we just wiggle it a little bit, then we also get an irreducible polynomial. And if we wiggle that a little bit more, then we get an irreducible polynomial. So then almost all of the parametrizations that we actually get will give me an irreducible polynomial. Okay, so these are cutting out fields of degree n because they're irreducible. So now we need to prove that the actual we prove that the number of polynomials with escalating height h, cutting out a single field. So these are, the number of polynomials that are giving me the same field is going to be at most big O of y to the n. So we can take y to be big O of h, and this is coming from the parameterization that we wanted. So we have at most big O of h to the n of these. So this means that we have big O of h to the n polynomials that are giving me the same field. So now we just say, okay, the worst thing that can happen really with these polynomials is that for every polynomial that I take, like we're taking all of the multiplicities possible for each of these polynomials. So then we just divide by the number of polynomials that give me the same field, right? So then we get h to the c times c plus 1 plus d times d plus 1 over 2 minus n polynomials cutting out distinct fields. So now we not only have the fact that the polynomials are distinct, but now we also have the fact that the fields are distinct. So we have gotten rid of the two main problems that we had originally. So then the polynomials are going to have discriminant at most h to the n squared minus n. And the fields that they are generating will also have discriminant at most that. So then we just need to rescale to actually get the degree, the discriminant bound that we wanted.
So a question. So the exponent of that x at the bottom of the screen. So is that going to give us the clue on when the n is going to be admissible?
Not really. The n.
It's a different n, right? Yeah.
So the n admissible is coming there. I guess there are two things. One of them is parametrizable and the other one is admissible. So admissible means that the n is actually a degree that corresponds to a field that is being generated by an algebraic point coming from the curve. And parametrizable means that I can actually write this n as a combination of things that are coming from the curve, like the degree of the curve that we're getting from the parametrization that we have. Okay. Does that answer your question?
Yeah, thank you.
Okay. So this means that we have produced now, if we just do this change, sort of like this change of variable, we have this many polynomials. So these are, we have produced this many polynomials that actually generate different fields, and they all contribute to this counting function that we had. So then sort of like the last thing that one has to do with this is that we made a choice of A and B that was optimal, right? We chose it as small as possible, but we didn't do that with C and D. We just chose C and D the way that worked out, but we don't know if we were smart enough when we chose them to make the best choice possible. And probably we chose the worst thing possible, right? When we were writing the proof. So now what one needs to do is to optimize these constants. So I can write down the details here. So let me just write this down. So if we have this polynomial, like we started with, and I'm not gonna write everything. So we have f of a over b, and this is all polynomials in T, c over d. And then we said, okay, this is equal to the sum of this phi of a comma b. And then there's something else, d to the degree y of f minus. Right, the parameterization is giving me this. So we will need to require something like c times I, plus the degree of y minus f minus I, all of this times d has to be less than n minus the degree of the I, a comma b, for each, with at least of them being an inequality. And this is coming from the choices that we made when we were proving what is admissible and how do we characterize this admissible in terms of not only admissible, but also, sorry, I see something in the chat. Okay. Not only how do we characterize this parameterizable in terms of how do we actually make them admissible? And this is again just fudging everything so that we force n to be big enough so that we can give it a chance to actually be coming from the parameterization that we have. So we have to require something like this. So actually the optimal choice satisfies that C would equal D, and that this would be equal to n over the degree of f, the y degree of f, plus some big O of 1 over n. So this is the optimal choice that we can make. And then if we take this and we plug it in into our original equation that we had, which was here, then we actually get that we have x to the 1 over m squared plus big O of n. And what was m? Well, m was going to be the mean. So m in this case is going to be the mean of the degree x and the degree y of f. So again, we found that there are a significant amount of extensions that are coming from here. And this is with the optimized constants. So I'm going to now talk a little bit more about what we could do with this. So something that we would like to do is that we have actually found, let me just look at how many, the notation, oh yeah, the counting functions. So here we actually have a result that, you know, is for this, right? We found a bound on the number of fields that are coming from algebraic points on the curve. We made sure that we have the degree that we want, right? And then we also have the discriminant that we want. And then the next step in this whole problem would be actually to ask more in our wish list. And then we want to prove that the actual Galois group that we get for this degree extensions is as general as we want it to be, right? So that we're actually getting Sn as the Galois group of the corresponding extensions. And this is something that we have tried. And the way that one does this would be to use conditions on the coefficients so that we actually can generate the Galois group. And this is coming from when one is building I forget the name, but the point is that like we need to not only have a long cycle, but we also have to have enough small cycles guarantee that inside the Galois group. So again, we need to constrain the coefficients even more of our parameterization even more to guarantee that we will have in the Galois group the number of cycles that we need to generate the Galois group. And why have we not done that yet? And this is coming from the fact that because our curve is just only a plane curve and our parameterizations are just f of x comma y is 0, and our parameterizations for A and B and C and D are very general, then we don't have, we haven't had the patience, I guess, to prove that we can actually put conditions on the coefficients and enough conditions on the coefficients without constraining that much without taking out a lot of polynomials, so that we get Sn as the Galois group. However, there is some hope, right? Because Hilbert irreducibility tells me that the polynomials are sort of like as irreducible as possible. So if one tried to prove that the Galois group is actually Sn, I would hope that we aren't losing many polynomials when we constrain them, so that they can actually generate, so that, you know, the roots of them can actually generate the R, so that the Galois group is actually Sn. So I think that the asymptotic is going to be the same. I don't think that the asymptotic is going to change a lot, because putting constraints on the coefficients, at least I don't think that we will have that many constraints that it would actually take out something that is equivalent to a power of X. However, that is sort of, you know, work in progress. And the other thing that I should talk about maybe a little bit is about the Jacobians. So for the Jacobians, we actually do have a proof of the cardinality. And this is very similar to the proof of the cardinality that is in one of Robert's papers. But I actually don't, I'm scared of geometry. So actually I haven't looked a lot at the proof to make sure that it is, I think it's correct. I don't think I understand it enough to actually talk about it today. So I guess I'll stop here, and sorry for making you look at horrible math equations. But I guess the main takeaway of this talk is that if you are counting fields, sadly, we don't have anything better than counting polynomials. Like, we have done math for many years, and we still have just this very archaic way of counting fields, which is like, well, let's just count the polynomials. N, which is the degree of the field, that the field extension that we want, that is always going to be constrained by some sort of coefficients or the degree of the curve that we have. And then once we are able to describe N in terms of the curve and which ends can we actually write because of the curve that we have, then we make sure that we can build a parametrization that gives me an irreducible polynomial. Then Hilbert irreducibility tells me that if I jiggle or wiggle around this, then I get enough irreducible parametrizations. And then the last part would be to make sure that I'm not counting the same field many times and that I'm not counting the same polynomial. So then I get rid of those multiplicities. And then the last thing that one needs to do is go back and double check that if I actually made smart choices so that I can write the best bound that I can write. Yeah, so this is sort of like the summary of the horribleness of I and J's and little a, little b, little c, little d, and the same but big that you just saw. So thank you, and I'll stay here if anyone has any questions.
Thank you, Allechar. Are there any questions or comments?
Oh, I just want to shamelessly plug in that this is work that we did in Rethinking Number Theory, and Christelle is here. So she organized that workshop, and Catalina's here, and she's in the second edition of the workshop, and we'll have a third version of the workshop this summer. So if you are interested, I guess I should just post the website. in the chat. Where's the chat here? But this is going to be online, so it doesn't matter if you're not in the US, and that's the idea, that we can get different people from different places. So if you are trying to look for collaborators that are nice people, this is a great way of finding that.
Thank you, Allechar. I do have a question.
Yeah.
I think you said this, but I didn't, maybe I didn't understand. So with this last counting function, where you say like, well, what if now we add a G to the list of things we're going to read? So did you say that specifically you want to look at SN, or what? So what would be like the ideal group? Is there an ideal group that you want to look at? Or on the other hand, is there like a first case that you would consider?
Yeah, so I guess the first case would be SN. And that is because, at least from the previous papers, that is what has been parameterized. I don't necessarily know if, I know that there exist other parameterizations for other polynomials. It's just that in terms of, so like, what you would do is that you will use Newton polygons that are coming from the valuations to make sure that you have some cycles in your Galois group. So if you have, I don't quite remember, but it's like if you have maybe a cycle that is long enough and enough short cycles, then you can actually generate SN. So you're putting constraints on the coefficients to do this. And the parameterizations that I've seen are for SN, but I do know that there are parameterizations for other Galois groups. So I know that there exist parameterizations, I don't know, for AN in terms of this, Newton polygons. I just don't think that, as far as I know, I don't think that anyone has looked at that in terms of like this, not only counting, in the specific case of algebraic, curves, but it is something that one should look at. And why? And this is because, for example, in the case of quartics, whereas the Galois groups that are not S4 and D4, like those ones aren't enough, but D4 actually does have an asymptotic that is important. So then I do think that one should look at this, because there are probably some groups that would give you an asymptotic that is not, zero, that there are actually enough fields that have that as the Galois group. And again, like this could happen because it happens in certain cases when we're just counting, there is a paper that is counting D4 quartic extensions of Q, right? They find an asymptotic for that, whereas the other ones are just very small. So when one counts by conductor. So I think that there is something to look at there. I just have to learn more about Newton polygons to do this.
Thank you. Are there any other questions? Yeah, Ronald, go ahead.
Yes, thank you, Catalina. Actually, it's just a final comment from the organizing committee. I really want to thank you. Thank to Catalina and Adrián Barquero for organizing this interesting thematic session. Actually, well, this is not my area, but I found these talks really, really interesting. And I hope the audience did it as well. Thank you so much. Good afternoon.
Thank you, Ron. Well, thank you, everyone, for joining us in this session. And just to remind you, we have a second part of our session on Friday afternoon. So from 2 to 5-ish, mostly because we have talks by David Kroom and Juanita Duque Rosero. And then we have a plenary talk which is by Angela Robinson that's going to talk about cryptography. So that's also kind of related. So I hope we hope that we'll see you then. Thank you. Good afternoon.